I am asking you to join me in welcoming Tony Barr. He is the inventor of the SAS computer language. He also is a multiple inventor. He invented a machine for optimizing the use of lumber. He was a founder of 4 different companies, including Barr Systems, and he is the current president of AMORE. Join me in welcoming Tony Barr.
Well, I have thought about this idea for all my life. I mean, it really wasn't phrased as a model of reality, but how could you make a better computer language that more and more people could use, that younger people could use? I'm going to lead you through my various trials and errors and learning experiences and tragedies. And now I'm feeling the air. I'm going up. Well, I started off programming actually as a grad student at NC State, but then I got a job with IBM at the Pentagon. And I was in the basement of in the bowels of the Pentagon. I mean, there were rats down there actually. But I had a fantastic experience there. It was the first time to put the computer information into the computer. I mean, it had been on punch cards, and they were just putting it into the computer. I ran one of my little assignments was to write a program called the hierarchy program to sort all the units by Army, Navy, Air Force, 1st Army, 2nd Army, 3rd Army, 1st Battalion, 2nd Battalion, down all the way down. It had never been done before. And at 1/6 of the data was incorrect. That's the data we're running on. Who's the operational commander? Who's the administrative commander? 1/6 of the data was wrong. I mean, because you just couldn't get it right with the punch card with the old electromechanical equipment that they used. But anyway, that was the context. I worked on this formatted file system, and this is from the Transactions on Database, an ACM journal. And we had the formatted file system, a self-defining file system. And we were so big on self-definition. That was what we said. You know, at the start of every file, we had the dictionary of what was on that file, what the variable name was, what the columns were, whether it was numeric character. Anyway, that was a revolutionary thing at the time. And actually, the SAS dataset came directly out of that. Well, self-definition is a big thought, and it's a biblical thought. You know, we have Moses at the burning bush asking God, "Who are you? I am that I am." An ultimate self-definition. Well, every cell is self-defining, right? So self-definition is what we live with. And this is a statue from Winter Park of Albin Polachek's, and it's a man carving his own destiny. And he did it when he was 19 years old, and he was just obsessed, apparently, when he did this. He was expressing his own character, his own will. And you can see that at the museum down there. Well, things went black for me. I got fired. And essentially what the guy said, "We just can't have any more of this. You've done 50% of the coding, and I got to spread the work around. So you're going to sit at this desk and figure out how 2 computers can share one disk drive." Well, that's an electrical engineering problem. We really had no resources. You know, it was not the web then. And I guess I could have taken off and gone to the library maybe and done some library research at the Library of Congress. But anyway, I was depressed. And luckily, my old boss from NC State calls and says, "All my programmers have left. We're getting a new computer. Can you come back and reprogram the regression and general analysis of variance program?" So I went back to NC. Actually took the bus down that weekend. And I got the job, went back, and I was in heaven again. 3 years later, this is the first manual, SAS manual, and it got to be very popular. Well, in 1968, Harlan Mills came and gave a lecture in the Research Triangle Park, and the one lecture changed my life. He said that this Baum and Jacopini proved that you could write any program with just 3 structures: the block, the if-then-else, the do-while. And he's argued, well, these are easier for the mind to deal with. No more spaghetti code where you jump from here to here to here. So I took the challenge. I mean, he said that it's much easier. You can prove your program's reliable. So I started programming that way, and I corrected some of my spaghetti code. And I was doing everything in machine language, but I still wanted to have those loops nested. So to me, I thought it was awesome that somebody could give a talk and just change your life. In '76, after 10 years of work, it was quite a mature system, and we came out with this manual, and that was 1976, so it was an anniversary of our country, red, white, and blue, and we used the 76 on it. But I only stayed with the company for 2.5 years, or 2.5 years, I guess it was. And I said goodbye. And I thought, well, I will, I just mentioned I was the biggest owner of that company with 40%, and I was the chairman. So it's not that I was a small player in it at that time. Well, I thought, well, I will bring my lumber cutting machine alive. I'd spent unbelievable amount of effort to solve the two-dimensional trim problem without defects, then this two-dimensional problem with defects, and then to do the pattern recognition, to look for the knot holes, the wane, and whatever in the lumber. And you take this raw lumber, and you run it through the rip and crosscut saw, and you make the dimension parts to make the furniture. But they lose a lot of lumber cutting around the knot holes. So I thought I would do that. And I actually went off and took a course on digital electronics and learned how to do my own electronics. It was a 5-day bug book course at VPI. But I spent $150,000 in 1 year, and I had only $190,000 left. So I had to do something. So I borrowed, I think, about $80,000 from my sister. At that time, we were in a hyperinflation, and house loan was 17%. I gave my sisters 20% interest. And I paid it back compounded, so they did all right by me. Well, I decided that I was going to write some software that'd be manservant. And I was fascinated with Robinson Crusoe, and in that, he had this very loyal, competent servant, his man Friday. Now, this just happens to be the way they portrayed him in one of the versions. Well, I needed to go and look at the fundamentals. I wasn't going to just write another language. I was going to do something revolutionary. So I studied Chomsky, Bertrand Russell, and well, I guess here's Chomsky. And I read Chomsky's book on syntax. And in that, he talked about the underlying grammar of language. Well, and he didn't know what it was. He said it must exist because all the languages have such regular patterns. So I said, well, maybe I can discover what the underlying grammar is. And so that was just my fantasy, but I read this guy's book, and he had the grammar of grammar in it. It was actually called the BNF of BNF, but I called it the grammar of grammar. And I thought that's a fascinating thing. And I thought, well, that I could write a editor that was controlled by a grammar, and you would not be allowed to enter an incorrect statement. You would not have syntactical ambiguity because you always had one finger in the grammar telling you what you could enter in, and one finger in the object. So the general thought is the grammar of grammar could be used to generate the grammar of language X. Then with the grammar of language X, you could generate objects. It's essentially generating the parse tree. And the grammar of grammar was itself a grammar, so it would define itself. So you could traverse through it and go for every element in it and it would give it the answer to what you were looking at in terms of itself. So it was some circular definition, but everything was defined. Now this fully defined world, we've never had such a thing. But I was in love with the idea that we'll have a fully defined world. And I got this going. And I thought it was amazing because people could see stepping through the grammar, and you could essentially see the parse tree as you went through from piece to piece. Actually, I had the underscore would go underneath the noun phrase, you could say, and then underneath the noun. And so at the bottom it would say noun or noun phrase. So it was I thought it was incredibly quick to understand what language was about. Well, the problem was this was a toy, and it was nowhere near a product, and now I'm 4 years without an income. So this is when I went and borrowed money from my sisters. And we moved the company down here to Gainesville, and this was expressed, this is probably from 95. Well, I know it was from 95. This was the cover of our magazine. We were publishing a magazine 4 times a year, all about the neatest things in our company. And this is me down here. Zane's still with the company, and Deborah's still with the company, and Ron Van Aken's with a daughter company of it. And this fellow here is kind of my genius programmer. He actually did the unbelievable, he had never done any electronics before, but he did a field programmable gate array thing that did the IBM channel, which is considered to be very difficult bit of electronics to do. And the amazing thing, I just tell you how this was. We sold that product for I think about $7,000. And you buy a PC, and the university was paying $3,000 a month to maintain a computer, just to drive some printers over in Tigard Hall. They got rid of that computer, $3,000 a month, put a compact computer in, our board in, so they had about a $10,000 investment. They paid it back in 3 months, right? So you can see how the world just bought this product like unbelievable. And so the Japanese were coming to see us, and the Brazilians went ape over it. We did 3 trips down to Brazil with it. Well, I got tired of being a manager, and I sold my company in 2012 to Gabriel Schwartzman. And he engineered the whole, he redesigned the company and came out with a new product. And then he realized he was too small to sell the new product, so he sold out to a bigger company, and then they sold out to Neurons, the company that makes the Siri software. So a nice bit of profit came out of that for me as well. Now I am pleased to have Joe DeWeese over here. Joe, raise your hand. Joe is my quality manager, and he and I put together a quality system, enterprise quality, well, I call it the Barr enterprise model. And we defined everything down in the company, down to how to restock the kitchen. So, and we had procedures for everything. And actually, we lifted people up because I had a guy in the shipping who really had no particular skills at all. But we had him doing all kinds of tasks. And one of the things we had him do is he opened the mail. If it was a check, he ran it through the machine, put it right into SunTrust Bank. And the point of it is that because we had everything very well defined, he could do 15 tasks where normally you'd only expect him to do 1 task and do it very well. Well, I'm working on this and ran out of money again, but no problem, you just go to the bank, right? I've got $6 million worth of assets in a building and, well, it's mainly building and land. So you just go to the bank. And I had about $2 million in other assets too. Well, it turns out that the rules completely changed. The bankers came back and said, you don't have any cash flow. The regulators won't let us loan. But the bankers said, if it was up to me, I'd loan you the money. I know who I'm talking to. But these guys up in Washington are making the decisions now. So taking all the judgment out of the local people. So anyway, out of money again. So I decided, well, I will develop a model of reality. This has been my idea. And this is the logo I came up with. And you remember the other one had 76 on it? The SAS 76 manual? Guess what that binary number is? Anybody have an idea? 1776. Phoebe has it. So, and navigating through knowledge space was my thought, because I thought, well, we could have a browser where you could just browse any structured knowledge. This is the knowledge that's in databases or in programs. And so that was my little tagline. But I got fascinated with object-oriented programming. And they say about object-oriented programming, it's the way we think. Now with this picture, some people see a pretty woman, some people see an ugly woman, and some people, their mind goes back and forth between the two. I don't think you can see both pictures at the same time. But it shows the way we perceive is in terms of concepts, and we're matching concepts with all the information that's coming at us. So we really are thinking in terms of concept and object. Now I sought some counsel out. I mean, I didn't, I had enough bruises that I still had my doubts about whether I could go forward with this idea. And I went to the Toastmasters, and a construction superintendent comes in who worked for Charles Perry Construction. And he gave a marvelous talk about their experience working down at the Digital Worlds Institute with James Oliveira. The architects don't get it all right all the time. And so the construction superintendents have got to solve problems. And they had big problems. And James Oliveira and this other superintendent came up with some marvelous solutions. Anyway, I phoned James Oliveira and said, can I come talk to you? And so we had a good time talking, and I told him I've got these worries. And he said to me, if you never go, you'll never know. So then he said, if you do go, maybe it'll crystallize the issues and the solutions will come to you. And it was very helpful advice. Well, I go working away, and I get invited to the Christmas party at the Department of Clinical Statistics over at the university. And so I'm there talking to a retired doctor. He had been the head of clinical sciences over at FSU. So to make conversation, I said, well, I just read in this book about Gödel. Gödel was this mathematician who was considered to be the most famous one of the 1900s, and he was very famous for his proof that no system can be consistent and complete. And anyway, I was reading that book, and Gödel said that, you take set theory and replace the word set in there with the concept of a concept, and you could define all of logic. I didn't really know what he meant by that, but I like the term concept of a concept. It has some real guts to it. I've been using type of type, and I didn't like type of type. So I changed my thinking. I'm going to go with concept of a concept. Now, this doctor started drawing a concept map. He said, did you know about concept maps? And he said, you draw the concept, and you draw the other concepts that are related to it, and you do some lines and label the lines, and you develop a concept map. It's a fantastic educational tool to bring focus to the students. So I Didn't think much about it at the time, but I got home and I put into Google concept and connection. And guess I got 30 books back. Concept and connection, biology, concept and connection, history, concept and connection. Well, maybe academics have something, are in love with this way of breaking down knowledge. So then I go to Amazon and I find there are 300 books, concept and connection. So I think, well, maybe I need to change my vocabulary. You know, instead of variables and methods, which is the vocabulary used by computer science, then I'll just talk about connections, concepts connected to other. Now, here is a concept map. It turns out the home of concept maps is Pensacola, the guy who originally invented it, and they market a concept mapping thing. And so you have all the concepts and there's connections and you label the connections. Well, what I realized is that I guess the sun's in my eye there. What I realized that the concept map is pretty much the same thing as the data model that systems architects use in designing the UF database. They have a vocabulary that they use. You know, it's the data model and it's the schema that defines the databases. And they draw these pictures very much similar to this. So they're the same system. So here's just, you know, like the book's concept and connection. Well, you know, if you think about our brain, we've got 10 to the 10th neurons, and each neuron has 7,000 connections. It's concept and connection again. Now, I found this to be fascinating, is that Descartes had a series of dreams that really shook him up. And his dreams were that we had, well, knowledge is a series of interconnected truths that can be ultimately abstracted into mathematics. So he had this idea of the unity of knowledge. And it's pretty much the same idea as the concept maps, concepts and connections. Well, the start of it is the concept of a concept. And I believe that this is this is the gem right here. Now, I don't know whether this can exactly relate to it, but you have a concept has got a list of all the connections. And the first connection is talking about itself, it's connection. So here we have all the connections that are defined in this list. This is the trick why it becomes self-defining, because it defines the very first thing on its list is a list of connections. So this is just a bunch of definitions. Over here, this is the definition. Connection is a list of connections. You got every concept has a parent, which is another concept, and has a list of children. The children inherit connections from its parent, and they add more connections. Then this is the way to relate to the people, is that you put a description in with the concept, so that every concept you have a title, an abbreviation, an abstract, so you can document everything in your world. Like this is the absolute source. Everything comes from this one particular thing. So then you have a presentation function, because you want to produce images where people can relate to it. And then you've got representation, which are the nuts and bolts, and I don't think we want to go there. Well, what type of connections do we have? And the part that I would just say is golden, I think, you either have a connection that's a definition or a connection that's a reference. Now, underneath the definition, you have just an object of a concept. And then I have it laid out here. You've got countable things like you have a list of objects or a sequence of numbers 1 to 100. And then over here, you have references, somewhat different character. This is talking, these are references, these are definitions of objects, and these are references to them. You have the reference that starts at the concept of a concept and follows any one of the connections down. So you can address any place inside the system. Now, with an address, you can come down through all these definitions, and you can actually come down to another reference, but you can't go past the reference in the address. So the point is that the address gives a unique place for everything inside the system. The path is a shortcut where you start somewhat down in the context tree. An element just means that, the Cade Museum would have a list of all the people that are members. And if you're talking about the person coming through the door, they're an element of that list of people. So I think that this is a complete list. It's somewhat arbitrary, but it's enough to build a system on. Now, this I think is where I depart from the object-oriented programming in a very big way. I look at every connection is identically defined in terms of its structure, but it's located in several different places. You know, every soldier has a green uniform. So you've got the uniform connections, they're stored with the concept. Then you have the variable connections, which is what we're normally thinking, the variable that's in the object variables. It's different for every object. And then you do have a global connection, which means that you have one instance of this object in your world and only one. And then we have, I use this little plug together thing here. When you go into a program, the thing that in all programming languages, you resolve the argument down to an address, and you sort of bind that address to the parameter name, and that's how the subroutine locates the variable. So that is when you go into a function or going into a program. I think that this is an important difference from the way that we normally think of object-oriented programming. Now, here are the basic instructions in AMORE. And the first thing you have the connection instruction. Now, more commonly, people call it the assign instruction. You assign to variable x the number 35, we'll say. But I think you're making a connection between one object and another, so I use the word connection for it. And you have a block, which is a list of instructions. You know, calling a program, which would be a program instruction. And I have a construct. The simplest format of it is in this form. It's the if-then-else statement, you might say, but it really is much more powerful. And then there's the leaving a block or leaving some construct, and of course you need to return, and if it's a function, you need to return an object. So these are the basic instructions. And this is kind of an interesting thing. Phoebe told me she wanted these other things on a bigger screen. Anyway, because of this, I had to think about it. I started thinking about how am I going to write the interpreter for this system. You know, every language needs an interpreter. And what I thought was that really, this was just my inspiration. I'm still developing this thing, I guess, mentally. This is one of the last undefined steps. But the point of it is that if you have an interpreter for the language, how much does the interpreter have to know? The higher order constructs you can express in terms of simpler things, like these simple things here, if you can express them that way, then the interpreter only needs to know this. In a higher order construct, you define the meaning or semantics in terms of those lower level things. So the interpreter doesn't need to know the more complex stuff. This is just kind of pictures that you put on top of it. Anyway, actually, in most computer languages have macros, and this would be the counterpart, but this is doing macros at not as an add-on, but as an integral part of the software, of the language. Well, just repeating, here's the way I do a connection statement. It's by intention. You want total cost to look this way in the form. Now, here's the way you normally do it in a programming language. So you've got to get rid of the blank and arbitrary equal sign and semicolon. So the concept and the object look fairly much the same. And here's a simple-minded programming example. You got these details here. You got total cost, $17.76. You want to put dollars in here, $17.76 here. Here's a little program. And it's done essentially with pictures. They look still like forms. But here you're going to do the modulo, which gets the remainder 0.76. You're going to multiply by 100, assign it to, or connect that to cents. You're going to take total cost and take cents divided by 100, getting 0.76 again, and you get the dollars. This is the way it would be in an ordinary programming language. Now, I declare in this programming language, you have to take Programming 101, where they tell you about how you should indent, so you make the program readable. So you've indented the do end. You have a special notation for how you express a function. And then, well, the second one illustrates the fact that you have to know about operator precedence. The division happens before subtraction. With the picture, you always know that you do the innermost picture before you do the outermost picture. And then you have the thing where you can right-click on dollars. Somebody has a description of what that's supposed to mean, then you would have that. You certainly right-click on the red in here for the minus, and it would tell you what the minus function is about. So every last entity would be self-documenting. And Phoebe was talking about Dr. Boole, so Boolean algebra. So this is just the definition of the and the or in terms of what would normally be called a truth table, but I call them these, well, I actually call them decision tables. So here's the if then else. So you asking if the final grade is less than or equal to 60. If it's true, you repeat the 5th grade. If it's false, you graduate to the 6th grade. With any instruction, you can put a description of it in, and if you click on that, you see the instructions that are behind it. So you could have a lot of code behind that if the semantics required it. And here's sort of putting together ands and ors together. Here we're saying if you're a teenager, grade point average is a 3.0 or more, or your SAT is above 1200, or you're special, you're true, you go to college, or false, you stay in the 9th, stay in the 12th grade. Now, important thing is how do you get rid of the parenthesis? Actually matching up parentheses is a real chore when they get to be 4 deep. So, but here we do everything with a picture inside a picture. We don't have parentheses. But if you have a binary function that is commutative, a plus b is the same as b plus a, and associative, it doesn't make any difference whether you add a to B and then that to C, or you first start off with C adding it to B and then back. If it has the property that they're commutative and associative, you can always do it over a list. So that works for and or, multiplication, addition. So you get rid of the parentheses. And it turns out the only place you use parentheses is in these situations. So we've eliminated something that the kids have to learn and they have trouble with. Well, this is a trick thing that, at least in the old days, everybody would say, well, you got a new language, does it do recursion? Can a function call itself? And the general example is factorial, which is n times n minus 1 times n minus 2 times n minus 3. Well, we do it in a single instruction here. We return the result of this, which is if n is greater than 1, if it's true, the answer is n times factorial n minus 1. If it's false, it's a 1. And this is the greatest common divisor routine. So we want to get the common divisor between x and y. Well, we make copies of that, and we compare a to b. If it's less than, we take b as b minus a, and if it's equal, we're done. And if it's greater, then we take a minus b, and we return a. And this is the way it looks in a programming language. So I don't say that this is so hard, but the fact that people can understand this just by right-clicking on any level of the picture means that the little kids can learn. And the big kids can too. Now, my question is, if this is easier on the brain for little kids, isn't it going to be easier on the brain for big kids? Now, it takes a little bit more space, but maybe we deal better. You know, there is a theory that we're visual thinkers for the most part. So maybe we do better with using pictures. I guess just repeating myself here, but I feel that this concept of a concept is the biggest takeaway idea of this, is that you can have a self-defining system that through inheritance you can build more and more complex functions. You can build everything using this. And we separate the presentation from the representation. So you can have the computer do your drawing. And you don't have to be so neat expressing your mathematical statements. The computer will draw it for you. So I think it'd be easier for people, and especially the kids. Now, on presentation, I just put, obviously you would use the color palette. You would, I don't know why I put this in here, but I haven't really done that much thinking about how to do a fancy presentation software inside of AMORE, but I feel that would come with further research so that you could do everything inside the same structure. But every puppet has this curiosity. Who's pulling my strings? So this puppet asked somebody else, and he said, another puppet said, it's a bigger puppet. Well, who's pulling that puppet's strings? Well, it's always a bigger puppet. Well, that's a complete story, because you always know you can just go up, 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 and there's always a bigger puppet. Well, this kind of illustrates that. Always a bigger puppet. Now, the point of it is that you want to have a finality with these things to know the truth. And you can have that little statement, there's always a bigger puppet, and you know the truth. Now, if you know the way the first puppet works, and you know the second one, you know the whole story. Well, in the terms of AMORE, we need an interpreter to interpret an instruction. Well, we define that, and but then who's interpreting the interpreter? Well, another interpreter. So the point is, if you define this for one level and say the interpreter's being interpreted by another one, you pretty much nailed what's going on. It's always a bigger interpreter. Now, I think that there are bigger issues in the world than just the computer language. You know, it's how do we think? You've got in philosophy the theory of the mind. How does the mind work? We need better models. It'd be nice if we could, the model that we use to program was similar to the way the mind worked. We'd be able to better talk about theory of the mind in terms of the programming model. I believe I've created something that is analogous to the mind. It's infinitely scalable. I didn't go into that, but the fact is that when you have one of those paths, you know, if you're doing an element of list that's 65,000 entries long, that only takes 16 bits. And if you go 10 levels deep, you about have the number of well, certainly the number of people in the world, and probably a lot more than that. The point is that you have a mechanism where you could express the whole world inside this. Now, obviously, there are issues that I'm not touching at all. I'm just thinking that this is a conceptual model that then you can map on the resources that the world has. So we got philosophy, psychology. How do we think? Well, we think in terms of concept and object. It's obvious to me, and even I guess over in Switzerland, they have $1 billion project, which is mapping the brain. And he pretty much says the same thing. He says that we have it's all these decisions that are made in our consciousness, and we got the whole world inside our brain that we're able to access through our consciousness. Then we have I actually, it's kind of a silly thing, but you know, I looked up finite state machines before I came here. I thought, well, maybe that might have. I'd actually thought that my little idea, my interpreter, was a finite state machine. I'm reading that finite state machine, and they're talking about parsing a bit stream. Well, it's the whole thing that you're bound to fail with syntactical ambiguity if you're dealing in terms of syntax. It just won't work when things get too big. So that finite state machine stuff was done years ago, and the Turing machine was done years ago, before we even had a computer. And sure, it does a lot of mathematical proofs, but it's proven that it's doomed to failure by at least Girdles' incompleteness theorem. Well, I guess I was just restating this thing about a system. Now, actually, this is a point that slightly troubles me. You've got Girdles' theorem, and the popular interpretation is no system can be consistent and complete. Well, it's saying that there's no truth in the world. It bothers me. But really the correct interpretation, no system defined by syntax can be consistent and complete. And I think Gödel was saying that. It was a direct attack on Principia Mathematica and related systems. So I think that our world has drifted from, at least the way that Gödel was thinking, Gödel was an incredible thinker. He was seeking the truth in everything he did. I mean, he was an obsessive guy. Well, we want to put the world back together again. You know, we have so many different languages that we program in. We have so many different databases, presentation languages. It's a very complicated world to program in. And I found this to be incredible. Everybody's talking about the Python language. So I said, well, I ought to study that. At least a third of it is character manipulation so that they can go inside a PDF and suck data out of it or whatever. And the point of it is it's all grunt work. It's work that we shouldn't have to do. The data ought to be just there where we can access it. We ought to be able to live with the data, not have to go and parse all this cruddy stuff. It's a grunt work. So well, on a positive side, the Cade Museum teaches people to program with pictures, and this is the Scratch program. And 30 million 12-year-olds have learned to program with Scratch. And some of these little 12-year-olds have written programs 1,000 lines long, real programs. So the pictures do make it easier for the kids. Now, Google has a project called Google Blocks, and they put a front end on top of a syntax-oriented language, and they program with blocks. It's for kids as well, but it enables people to see these programs visually with blocks. So the idea of the visual representation is already taking over. Now, to make any system, you have to put an authority structure on top of it. Who's in charge of the major definitions? Who's in charge of the schema of the University of Florida? And then you get down to some little level where you've got control of your concepts. So you have to have an authority structure. Then you also have to have a trust mechanism so that people can do transactions. I'm just saying there are so many big issues that to make this AMORE thing a reality that where we all lived inside it. I mean, to me, I think it's a 20-year plan, a 20-year effort. And actually, I even think that the older people will never put up with pictures. They like their strings of characters. And then obviously you have to scale it. You have to figure out how to partition the underlying bits and bytes such that people have control of their own part of it, and so that you can actually scale it so that it spans the whole world. Well, one day Jonathan meets two gulls who take him to a higher plane of existence. That's my talk.